Let's take a look at the kinds of attractive forces, intermolecular attractions. Temporary polarity in the molecules due to unequal electron distribution leads to attractions called, and here's the first category, dispersion forces. I've often heard of this called London dispersion forces. It's a person's name. Okay, so let's underline temporary. Permanent polarity in the molecule due to their structure leads to attractive forces called dipole-dipole. Remember, a bar magnet is a dipole, areas within the same structure that have positive to negative. To highlight the difference between dispersion, these are temporary. Dipole-dipole are permanent polarity. Especially strong is the third attraction called hydrogen bonds. Hydrogen bonds is an extremely strong electronegative atom attraction. If we have a hydrogen attracted to an oxygen, a nitrogen, or a fluorine, from one molecule to another, a hydrogen attracted to oxygen, nitrogen, or fluorine, those are the three most electronegative elements, we call that attraction a hydrogen bond. It's not a true bond, that's why I'm drawing dashed lines instead of a connecting straight line. An attraction will see the dashed bonds. The three categories of attractive forces: dispersion forces, which is a temporary polarity, a dipole-dipole, which is a permanent polarity, and the strongest of all is very unique to a hydrogen being attracted to either nitrogen, oxygen, and fluorine. Hydrogen on one molecule, strongly attracted to a very electronegative element on the other. Let's talk about the first category of intermolecular forces known as dispersion forces. Again, to repeat a definition, these are simply fluctuations in the electron distribution in atoms and molecules resulting in a very temporary dipole. The key here is that they're temporary. In a region that has excess electron density, we're going to see it develop a negative charge. In a region has a depleted electron density, it will have a positive charge. The attractive forces caused by these temporary dipoles are known as dispersion forces. I always hear them called London dispersion forces. Every molecule, every atom will always have the ability to distribute a dispersion force. A temporary dipole is established in one molecule as it induces a pole in all surrounding molecules. Every atom and every molecule, if it becomes so close to another, it can temporarily create a region of positive and negative. A dispersion force manipulates electron density temporarily. Here's a nuclei of a helium atom. 2 protons, 2 neutrons, here are its 2 electrons. If at a particular moment in time both electrons are near each other, that creates a distribution that's a little bit negative on one side, a little bit positive on the other. If we see one helium atom with an electron density of a negative cloud coming near a positive cloud, we set up a dispersion force. Notice they're doing a little dashed line. It's a weak attraction that's a temporary attraction just based on manipulating electron density. An instantaneous dipole on any one helium atom may induce an instantaneous dipole on a neighboring atom, and then you see this attraction. It's temporary. It does not stay in this position. Soon as these electrons become so close, electrons repel. This will go back to an equal distribution. Dispersion forces are very temporary. The magnitude of the induced dipole depends upon several factors. Polarizability of the electrons, which is really talking about the volume of the electron cloud. The larger the molar mass, the more electrons that atom has, the bigger the atom are. The larger the electron cloud becomes, the more we can induce a dipole. Increased polarizability just means an induced dipole equals stronger attractions. Bigger atoms, heavier atoms, stronger dipole inducement. The shape of the molecule can also influence a dipole. If I have more surface-to-surface contact, a larger induced dipole equals a stronger attraction. The larger the molecule, the larger the attraction. Long hydrocarbon chains will have a better induced dipole. So in this particular graph, I know there's some overwriting here, but let's make some sense. These are the noble gases, and the molar mass is definitely increasing as the size of the atoms increase. They get heavier as you go down a column. I can clearly see that the boiling point follows that same attraction. The larger the atom, the greater the London dispersion force, again due to the manipulation of the larger electron cloud. The stronger the dispersion force creates a higher boiling point. Molecules have a greater attraction to each other the heavier they are, and therefore will have a higher boiling point. Heavier the molecule, the bigger the molecule, the stronger the dispersion force, the higher the boiling point. Relationship between boiling point and molar mass of nonpolar molecules, such as those noble gases, halogens, or this is just any element, XH4, could be like methane. You can see a clear distinction. Boiling point definitely increases as the molar mass increases. Going from left to right on a period, the atoms are getting heavier. Boiling points will increase. Properties of straight chain alkanes. 1 carbon in methane, 2 carbons in ethane, 3 carbons in propane, 4 carbons in butane, 5 in pentane, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1 carbon being added each time to the hydrocarbon chain. What we notice is a trend. The bigger the molecule, the heavier the molecule, the higher its molar boiling point. MP stands for melting point, again steadily increases. And its density will increase. The heavier the molecule, the more London dispersion force, the greater the attraction between the molecules. There's more electron density to manipulate to create a dipole moment. Pentane with 5, hexane with 6, heptane with 7, octane with 8, nonane with 9 hydrocarbon chains. Those numbers of carbons. Molar mass will increase. The heavier the molecule becomes, the higher the boiling point. The stronger the intermolecular London dispersion forces. Same trend. As molar mass increases, boiling points increase, melting points increase due to the strong intermolecular attraction. The effect of molecular shape on the dispersion force, and again, think about surface area. The more surface area we have to come into contact between the molecules, the stronger the dispersion force will be. So if I have a long hydrocarbon chain versus one that's kind of more circular, long drawn out, or more around a central atom, notice the trend. The molar mass, they're pretty equivalent, 72.15 for pentane. But in neopentane, 72.15. Let me kind of draw this to make sure we're understanding. This is a long hydrocarbon chain, just 5 carbons in a row, and those are hydrogens coming off like this. So a long carbon chain is a long surface area. However, here in neopentane, they arrange the carbons a little differently. They attach them back to a central atom, 1, 2, 3, 4, 5 carbons. But instead of in a straight chain, they've got them arranged back to the central atom. And yes, there's still hydrogens coming off there. So it's the same number of atoms, just rearranged a little differently. The longer the chain, the more opportunity to create surface area contact, and therefore more London dispersion force, and therefore a higher boiling point. Same molar mass, different arrangement. The one that has more surface area creates more intermolecular attraction and will have a higher boiling point. Clearly, normal pentane, N-pentane, 5 in a row, boils at a higher temperature than neopentane, less surface area to create London dispersion forces. Branch chains have lower boiling points than straight chains. The straight chain isomers have more surface-to-surface contact and therefore create more intermolecular attractions, more opportunity to induce a dipole called a London dispersion force. Choose a substance in each pair with a higher boiling point. We're asking ourselves, thinking about molecular mass and surface area. Here we have a methane molecule, CH4. Here we have a butane molecule, C4H10. Clearly the molecular mass is larger in the second structure. Higher molar mass, larger surface area will create more London dispersion forces and therefore a higher boiling point. Pick the heavier molecule, long straight chain. Now in letter B, C6H12 is the same formula. One of them is a long carbon chain and the other is a cyclic structure. More surface area creates a higher boiling point. Less surface area, less intermolecular attraction, a lower boiling point. We selected correctly. The effect of dipole-dipole attraction on boiling and melting points. Dipole-dipole attraction. I missed a slide. We're missing, there we go, there's the slide. The second category. Let me pause the slide here and just get this all settled in. So I'll pause and start again in a moment. The second category of intermolecular attractions is a dipole-dipole attraction. Remember, all compounds, all molecules, all atoms have London dispersion forces. This particular category, the second category, dipole-dipole, only occurs between polar to polar molecules. Polar molecules have a permanent dipole. London dispersions were a temporary induction. These are very permanent. Based on the polarity and the shape, we create these oppositely charged regions of a molecule. They are not temporary. They're based on molecular geometry. So we see regions of a molecule just based on its structure and electron density that have a region of positive and a region of negative. We can clearly see this region here being what's called a dipole-dipole attraction. The negative moment on one molecule being very strongly attracted to the positive moment on the other. Opposites attract in a polar molecule. The permanent dipole adds to the attractive forces between the molecules, thus even raising the boiling point and melting points even higher. Polar molecules boil much higher than a nonpolar molecule. The effect of dipole-dipole attractions on boiling and melting points. Thinking about a structure, CH2O, very equivalent molar masses. CH2O is formaldehyde. We used to use it as a preservative in biology class. Molar mass of 30.03. Ethane is C2H6, molar mass pretty close to the same, 30.07. Based on the formula weight alone, I wouldn't be able to predict what boiling point would be higher or lower. But if I look at the structure, I can clearly see the formaldehyde with its electron pairs up here on the oxygen, giving this region a little bit negative, these regions a little bit positive. The molecular geometry would be trigonal planar, 330. Very polar structure. Ethane is a nonpolar molecule. There's nothing unique in this particular structure at all to make one area positive, one area negative. Based on the same molar mass, but one being polar, look at the difference in boiling point and melting point, significantly higher for the polar molecule than the nonpolar molecule. The dipole-dipole attraction creates a strong intermolecular attraction and thus increases the boiling and freezing points of our compounds. Here's the same idea. The molar mass of these compounds, very similar. However, the polarity of these molecules, very different. The nonpolar molecule, -42. A symmetrical molecule with oxygen at the center atom, a lone pair, but it's very symmetrical, -24. Oxygen versus nitrogen is what I'm seeing as the difference here. The electronegativity difference here is going to create a higher boiling point. We can clearly see the more polar the molecule, the more electronegative the molecule is, the higher the boiling point, due to the dipole-dipole interactions. To determine if dipole-dipole attractions occur between CH2Cl molecules, I really just decide, is this a polar molecule? We started by finding the electronegativity value for carbon, 2.5. Each hydrogen was 2.1. Each chlorine, 3.0. We're trying to find if there's dipole-dipole attractions. We're trying to find if the bond would be polar. This formula for the Lewis dot structure takes the electronegativity difference into the shape of the molecule. Looking at the shape and just kind of going down here, this region on the molecule clearly shows a negative region. The molecule up here clearly shows a positive region. Without ever looking up electronegativity values, this particular structure clearly shows a region of negative and a region of positive. And as soon as I recognize it's not perfectly symmetrical, then I would have a polar molecule. And therefore, yes, every polar molecule would have a dipole-dipole interaction. If I replace these chlorines with hydrogens, perfectly symmetrical, no dipole-dipole, it's nonpolar. If I did a carbon tetrachloride and made all of the bonds going back to carbon, if they were all chlorines, perfectly symmetrical, it's nonpolar, so no dipole-dipole. But the original picture clearly showed an area of negative and an area of positive, making it a polar molecule, so yes, dipole-dipole. Predict the compound in each of the pair with the higher boiling point. CH2 with an F, connected to a carbon, couple of H's and an F. Here we have something called a fluorine on the same carbon and a fluorine on the opposite carbon. So taking a look at the structure, I can just go from here to here. We can see clearly the answer that way. If the structure shows symmetry, I can literally flip this carbon and find it to be symmetrical. The area on the fluorine would be negative, but it's balanced by this area on the fluorine over here, which is also negative. It's symmetrical. But over on this side, I clearly see when the fluorine's on both sides, this region, the entire right side of this molecule will be negative. There's nothing unique over here, so it ends up to be positive. This molecule is more polar, therefore will have a higher boiling point. So the arrangement, notice down here the chlorines in the cis version of dichloroethane, if both chlorines are on the bottom versus one top, one bottom, this is a symmetrical molecule. The negative on this chlorine is being balanced down here. I can flip it and create the same molecule. Clearly, if they're on the same side, it's not balanced, positive and negative within the region. This molecule is more polar and therefore will boil at a higher temperature. Polar, nonpolar. Polar every time will have dispersion forces increasing the boiling point. Our third category of intermolecular attractions is called hydrogen bonding. When a very electronegative atom is bonded to a hydrogen, it strongly pulls the bonding electrons towards it. Hydrogen attracted to an oxygen, a nitrogen, or a fluorine. These are the three most electronegative elements. Because hydrogen has no other electrons, it's pulled away, and the nucleus becomes de-shielded, unprotected if you don't like that word. So it's exposing the hydrogen proton. A little proton really is, this is a picture of a little hydrogen atom. It's one positive proton, one negative electron, and if I steal its electron, I'm exposing that positive proton. And it creates a very strong positive core, a positive attraction. That hydrogen bond is that exposed proton being very attracted to either a fluorine, a nitrogen, or an oxygen. The attracting of electron clouds from neighboring molecules creates the strongest attraction of all is a hydrogen bond. So hydrogen bonding, when hydrogen is directly exposed to a fluorine, oxygen, or nitrogen, the bonding atoms acquire relatively large partial charges, giving rise to strong dipole-dipole attractions. A hydrogen bond is between molecules, the hydrogen on one molecule being very strongly attracted to the fluorine on the other. The hydrogen on one molecule being very strongly attracted to the fluorine on the other. This here is the strongest intermolecular attraction known as hydrogen bonding. Hydrogen from one being attracted to either a fluorine or a nitrogen or an oxygen. That's it for hydrogen bonding. Those strong electronegative elements, F, O, or N. Hydrogen bonding exists in water and thus gives us one of the highest boiling points for a liquid at room temperature. The hydrogen on one molecule very strongly attracted to the oxygen on the other. This here is a hydrogen bond, this very strong intermolecular attraction. H from one molecule attracted to the O on the other. Here's yet another hydrogen bond. Hydrogen on one molecule attracted to the oxygen. Here in our slide number 50, we're being asked, of these compounds, one is a liquid and the others are gases. Which one and why? Of these compounds, one of these compounds is a liquid and two others are gases. Which one is a liquid and the other are gases? I got it out that time. So we're just taking a picture of a formaldehyde, C double bond O and single bond to H's. We have fluoromethane, carbon single bond hydrogens and a fluorine. And hydrogen peroxide, H2O2. What I clearly see here, again with these oxygens, I can see a hydrogen connected to an electronegative element called oxygen. We are discussing hydrogen bonds. Hydrogen has to be either attached to an O, hydrogen attached to an N, or hydrogen attached to a fluorine. The oxygen hydrogen in formaldehyde, although they're in the same compound, they are not attached to each other, so no hydrogen bonds. And again, although we have fluorine and hydrogen within the same compound, they are not attached to each other, so no hydrogen bonds. And therefore, the only one where we have oxygen and hydrogen attached to one another and can set up the polar bonds of a hydrogen type connection is the hydrogen peroxide. When I see that hydrogen bonds can form, they have very strong intermolecular attractions and therefore will be a liquid. The two compounds that do not have hydrogen bondings do not have strong intermolecular attractions and therefore would be labeled as gases at room temperature. And the slide is well printed over, but in the PowerPoint it's an overlay slide. You can see those words appear one at a time. Same idea here, choosing the substance in each pair that is a liquid at room temperature. It's asking me who between the two has stronger intermolecular attractions. Here I'm seeing methanol, CH3OH, where the carbon has a single bond to each of those hydrogens and then an oxygen hydrogen. Here, I have carbon attached to a carbon, giving us a structure that looks like this. Carbon, single bond carbon, where the hydrogens are coming off of each carbon here, and then 2 fluorines here. Clearly, the hydrogen attaching back to the carbon eliminates no hydrogen bonding, and therefore will be a gas at room temperature. This compound will form hydrogen bonds and therefore will be a liquid at room temperature. Stronger intermolecular attractions when the hydrogen's attached to an electronegative element. Here's an ether, CH3O, CH2, CH3. Structural formula here shows, although the compound both contains hydrogens and oxygens, they're not bonded to one another, no hydrogen bonding. Most likely a gas at room temperature. However, here we have a carbon, CH3, carbon, CH2, another carbon, CH2, and then a nitrogen, NH2. Clearly, I see a hydrogen attached to an electronegative element such as nitrogen, and hydrogen bonding can form. Therefore, this would be a liquid at room temperature. The hydrogen must be attached to either an N, an O, or an F, so that between the molecules we can set up hydrogen bonding. The attractive forces in solubility. Solubility depends in part on the attractive forces of the solute and solvent molecules. The old saying goes, like dissolve likes. Polar will dissolve with polar, nonpolar with nonpolar, but the two opposites will not dissolve. They are said to be immiscible. Liquids that do dissolve in one another are known as miscible liquids. Likes dissolve likes. Polar with polar, nonpolar with nonpolar, but not the opposite. Many molecules have both a hydrophilic and a hydrophobic part. Hydrophilic would mean water-loving, polar. Hydrophobic would mean water-hating, and that would be a nonpolar end of the molecule. So solubility in water becomes a competition between the attraction of the polar groups for the water and the attraction of the nonpolar groups for their own kind. And we'll see that happen in long chains of hydrocarbons. Pentane is a nonpolar molecule. We have 5 carbons in a row. Each one of those fills out its octet with hydrogens, a molecule of pentane, C5H12. Since this is a completely nonpolar molecule, water is indeed polar. There is no attractive forces between the water and the pentane, therefore no solution forms. We literally see a layer, just like oil floating on water. Pentane would float on water, and they would not mix between them. So immiscible liquids do not form a true solution. They are not soluble. Nonpolar pentane with polar water will not form a solution. However, polar solvents with water certainly will form a solution. The polar solvent, let me get that down a little bit, that might be easier to read. The polar solvent hydrogen bonds with the water molecule. Here is a polar solvent called dichloromethane, or ethylene chloride. Same idea. 2 common names for the same compound. If I place that into another polar molecule, such as water or ethanol, there are oppositely charged areas of each molecule, and a solution would indeed form based on the hydrogen bonding setting up between the molecules. With nonpolar solvents, such as hexane, toluene, carbon tetrachloride, nonpolar solvents are very good at dissolving nonpolar solutes. Likes dissolve likes. We have a 4th category of intermolecular attractions. We started with London dispersion forces, number 1. Number 2, those were called dipole-dipole attractions. Number 3, hydrogen bonding. And now the 4th, intermolecular attraction, is called an ion dipole attraction. In a mixture, ions from an ionic compound, metal to nonmetal, positive to negative, cation to anion. Those compounds are attracted to the dipole of polar molecules. The strength of the ion dipole attraction is one of the main factors that determines the solubility of an ionic compound dissolved in water. Sodium chloride is ordinary table salt. Sodium is positive, chloride is negative. When sodium chloride dissolves in water, it dissociates. It lets go of the ions, and we can clearly see the attraction between oppositely charged areas. The sodium gets aligned with the water. The chloride gets aligned with the hydrogen. The oppositely charged oxygen surrounds the sodium ion. The oppositely charged hydrogen surrounds the chloride ion. This process was what we labeled earlier as the process of hydration or solvation, dissolving an electrolyte into water. Choose the substance in each pair that is more soluble in water. Water is polar. Let's find the polar molecule. When we think of methanol, CH3OH, here is a hydrogen bond that can attract to the water molecule. This would be a hydrogen bond setup between methanol and water, a very strong intermolecular attraction. CH3CHF2 does not show hydrogen bonding. Therefore, the more soluble molecule is the one that exhibits the stronger intermolecular attraction, which would be the methanol. Here in this picture, we have a long hydrocarbon chain. 1, 2, 3, 4, 5 carbons. This is called pentane. Clearly a nonpolar long-chained carbon versus methyl chloride, CH3Cl. Clearly I see the area of polarity. More polar molecules are water soluble. The more soluble here, CH3Cl. Clearly nonpolar will not mix with water. The polar molecule will. Likes dissolve likes. So in summary, dispersion forces are the weakest of intermolecular attractions. Dispersion forces are present in all molecules. The magnitude of the dispersion forces increases with molar mass. Polar molecules also have dipole-dipole attractive forces. Hydrogen bonds are the strongest of the intermolecular attractive forces. Hydrogen bonds are present when a molecule has hydrogen directly bonded to an oxygen, nitrogen, or a fluorine. Only example of hydrogen bonded to fluorine is HF, hydrofluoride. Ion dipole attractions are present when mixtures of ionic compounds are dissolved with polar molecules, such as salt water. Ion dipole attractions are the strongest intermolecular attraction, and the ion dipole attractions are especially important in aqueous solutions of ionic compounds, commonly called salts, made up of a positive metal, cation, hooked to a negative nonmetal, anion. Dispersion forces, dipole-dipole forces, hydrogen bonding, and ion dipole are all the types of the intermolecular forces.